This is Lynn Turback, and welcome to the second in a sequence of screencasts covering the second half of the Objects from Scratch lecture material from Friday, April 19th, 2013. In the last screencast, we saw how to write instance variable declarations and constructor method declarations for a simple Buggle class. In this screencast, we'll cover how to write instance method declarations. And we'll start with three right here. So the first one we ask you to look at is the getPosition method. You're well familiar with this method. It returns the position of the Buggle. The second instance method we consider now is the setPosition method, which takes a location and changes the position of the Buggle to be that location. And these two methods are representative of other similar methods that we will not write. For instance, the getHeading setHeading pair is very similar, or getColor setColor is very similar. So once we understand how to deal with getPosition setPosition, we'll know how to do many other simple Buggle methods. The third method we'll consider right now is not a Buggle method that you are familiar with, but it's one that we could add to the Buggle class if we wanted to. So in this method called setPosition as well, we have a different interface, one that accepts the X and Y positions rather than accepting a location for the new location. And again, this does not appear in the regular Buggle contract, but now that we're familiar with how to write methods, we could, if we wanted to, add it to the Buggle implementation. And let's also emphasize that in Java, it is possible to write numerous methods that have the same name, but differ in their types. So for instance, here we have two setPosition methods, one of which takes a single argument that's a location, and the second of which takes two arguments that are two integers. And that's just fine in Java. It can distinguish them by the number and types of their arguments. Now, what I would like you to do right now is to pause this screencast and to write on a piece of paper the implementation of these three instance methods. Okay, let's discuss the implementation of these three methods. The first is getPosition, whose definition is deceptively simple. All we need to implement getPosition is return this .pos. Okay, why does that work? Well, let's imagine in execution land we have some Buggle B2 whose position we want to get. Then when we say return this .pos, this is B2, and B2.pos is, in this case, the location 52, which is returned. Now this seems super easy, but in fact it's a bit subtle. And the subtlety has to do with the fact that, recall that the instance variable pos and the other instance variables are private. So it's not possible to access these instance variables by name in any other class, even in subclasses of Buggle. So you've written zillions of subclasses of Buggle this semester, but even in those subclasses you could not refer to the position by its name because it's private. So if we want other classes to be able to access the position of a Buggle, access its private position instance variable, we must access it through a method. So a method allows us to get access to the secret that is hidden inside of a private instance variable, because the getPosition instance method of a Buggle can access the private variables. So instance methods within a class can access the private instance variables, but nothing outside the class can. And because the instance method getPosition is public, it's usable outside the class, and it can thereby reveal what is hidden inside this instance variable. The definition of setPosition is similarly very simple. It's also a one-liner, like many instance methods. It's just this .pos gets lock. And to understand why this works, let's consider trying to set the position of Buggle B2 to 76. When we create the execution frame, it has the local variables this and lock. And this .pos get locked, this is B2, lock is 76, and we are setting the pos variable to be 76. Again, because the pause variable is private, if we wish to be able to set it outside of the Buggle class, we must provide a method like setPosition that's public, that allows us to perform this action. If we were to provide getPosition but not setPosition, we would be able to access the variable but not change it, thereby making positions of Buggles being immutable. So we see that methods can control access to private instance variables. As our third example, we'll consider the second version of setPosition, in which we provide the x and y coordinates independently rather than providing a location. And this has a similarly simple definition. This dot pos gets new location xy. For example, suppose we set the position to 3, 8. Then in the execution frame, we now have local variables x and y, which are used to create a location, and then we change the location to 3, 8. That completes the definition of our first three Buggle instance methods on slide 16. Let's move on to slide 17, where we consider the left and right instance methods. Now, one way to implement a method like left would be to use conditionals. We could, for instance, imagine saying that if the Buggle is currently facing east, change its direction to be north. If it's facing north, change its direction to be west, and so on. It turns out we don't need to do that because we can leverage already existing methods in the direction contract. So for instance, the direction class already provides an instance method itself called left, so that if we ask the east direction for left, it returns north. If we ask the north direction for left, it returns west, and so on. So using these methods from the direction class, we can simply implement the Buggle left method by asking the Buggle to change its private instance variable dir to be the left of its current dir, and we can implement the right method in a similar fashion. To wrap up our discussion of Buggle instance methods, we'll consider two versions of the Buggle forward method. The first is the version of forward that doesn't take any parameters, that moves the Buggle forward 1 unit in its current direction. And as before, we could use conditionals here. For instance, if the Buggle is facing east, then we want to increase its x-coordinate by 1. If it's facing north, we want it to increase its y-coordinate by 1, and so on. But again, we can get some help from the direction class. So it turns out that one of the helper methods in the direction class is the toLocation method. And toLocation turns a direction into a location that has zeros, ones, and negative ones. So if we imagine that a Buggle is here in the center, then to the east, that's a coordinate that is 1 unit in the x direction, 0 units in the y direction. To the north, it's 0 in the x direction and 1 in the y direction. To the west, it's -1 in the x direction, 0 in the y direction. And to the south, it's 0 in the x direction and -1 in the y direction. So we could use that in our method by naming a local variable called delta that holds on to that information. And what we'd like to do is, if the current direction in the center square here is xy, we'd simply like to add the x and y components of delta to our current xy to get our new position. And here is the Java code that does that. We simply create a new location that adds pos.x to delta.x, pos.y to delta.y, and puts that in a variable called new pos. And finally, we simply want to set our private instance variable pos to be the new pos. Here we're going to have some extra code, a conditional that allows us to check that the positions are actually reasonable, that they're 1 or greater. If they're not, they must be outside the grid. So we'll add that little conditional, but the most important thing here is that we're setting the position of the Buggle to be the new position that we've calculated. So that's how we implement the forward method. How would we implement the backward method? It would be very similar. The only difference that we would need is that we would need to change the place where we add the delta x and delta y and instead subtract. So backward would be almost exactly the same as forward. We'll conclude our discussion of Buggle instance methods by considering the second version of forward, the one that takes a single integer parameter indicating how many units we want the Buggle to go forward. Well, if we want the Buggle to go forward by 3 units, what we effectively want to do is call the 0 argument version of forward 3 times. So we can implement this by using a loop. We can basically say as long as n is greater than 0, we want to call the 0 argument version of forward and decrement the n, and that will perform forward the correct number of times. That almost works, except if we want to handle negative numbers n. For instance, suppose we said we wanted to go forward -3 units. Well, that would be problematic because then n would never be greater than 0, and we would end up going through this loop here an infinite number of times. So that would be incorrect. So we need a special case to handle this, and we can do that by having a test. If n is less than 0, then we want to go backward -n. For instance, if I've asked to go forward -3, what I really want to do is go backward by 3. Well, this assumes that we have a version of backward that is defined. We saw before how to define the 0 argument version of backward, and we could define the 1 argument version of backward in the same way that we've defined forward here, simply by swapping the names forward and backward. So that would be pretty easy to do. So that concludes our discussion of Buggle instance methods. We're going to jump forward through the inheritance material now to go directly to the end of the lecture where we discuss class variables, because that's information that you need to know for your text turtle problem on problem set 9. For this material on class variables, please listen to the next screencast.